In this video, we're going to talk about numerical data, numbers, data types that hold numbers. And here is an example. We've talked about a couple of these already. We've talked about ints. So int is a whole number. Ints can hold values from -2 to the 31st up till 2 to the 31st minus 1. So any number, thousands, millions, -2 billion something to +2 billion something. Okay, so ints can hold some really big integers, okay, but they can't hold any decimal places. We also talked about doubles. Doubles can hold negatives up to -1.7 times 10 to the 308th power, including some really small decimal numbers. 4.9 times 10 to the -324th power. That's a lot of decimal places. And the positive range about the same distance on the positive range. So really big numbers with decimals, really far numbers with negative in front of them for ints and doubles. But what about these other ones? We also have some other data types we can use for numbers. We can use a byte. Okay, and a byte uses 8 bits of memory. That's 8 ones or zeros. So a byte will hold a number between -128 up to 127. Okay, we can use a numerical data type called short for variables that hold numbers. And they go from -2 to the 15th to +2 to the 15th minus 1. So about -32,000 something to +32,000. And we saw ints hold massively big negative and positive numbers, but there's actually a data type. These are all integer types. Byte doesn't hold very big numbers. Short holds a little more. Ints are pretty big. And there's also long. And long is a data type you might want to use with astronomical calculations or something, but it goes -2 to the 63rd power, which is a giant number, up to 2 to the 63rd power positive. Okay, so these are all integer data types. This one holds really long numbers. This one holds really short numbers. Int's the one we use, though. So I just showed a picture to some of my classes the other day of a TRS Model 80. It was a computer made back in the late 70s, sold by Radio Shack. And it was the first computer I ever programmed on. And they were surprised to see that the computer had 4K of memory, which is less memory than probably any image you've seen on Instagram. By far less memory. That's all you had to work with was 4K. So back then, using a byte was important, okay? Because we wanted to conserve that memory. We wanted to conserve space on our drives and our storage media, which was tape back then. So using byte would save memory. So you're really careful to only use the size that you needed. Now, today memory is cheap. So we don't very often see people using bytes and shorts to conserve memory. We just kind of make everything an int, even if we're only counting to 50. Okay, we could do that with a byte, but we just make it an int. So you need to know about these other types. There are times when we can use them. But generally, anytime we're using an integer data type, we use int. But you need to know byte, short, and long exist. Okay. There's also float and double. Both of these will hold decimals. Okay. Float is a 32-bit number, so it can't hold as big a numbers as a double, which is a 64-bit number. It holds massively more than a float will. Because floats don't hold as big a decimal places, you can get more rounding errors with floats. A lot of other languages, we default to floats. Sometimes it doesn't matter if there's slight rounding errors, and we use floats to make things faster in like game programming. But generally, in most Java programs, if you're using something with a decimal, you're going to make it a double. So we see ints for integers, and we see doubles for anything with a decimal, because we're not too concerned about saving the little bit of memory space now, because memory is cheap. Okay, so floats and doubles both hold decimals. Doubles hold bigger decimals. Byte, shorts, ints, and longs hold integers, but we almost always use ints. So how do we read those from the keyboard? Well, we saw scanners, right? We did this once. We created a scanner called input, and then we said, hey, input, give me the next, and we used a double for the radius on those previous projects we saw. But there are methods for every data type built into the scanner. So if I want the scanner to get me a byte, I can say next byte. If I want a short, I can say next short. If I want the integer, I would say next int. Get me an integer of the int type. Okay. Get me an integer of the long type. Okay. I can also use floats and doubles. But which two do you normally going to see? Probably next int and next double, because we use ints and doubles most of the time. But all of those methods exist in the scanner objects, so we can make use of them. Just know that it's usually going to be next int or next double, depending on whether you want decimals or not. Numeric operators. You're probably familiar with every one of these because you've been doing them since you could, maybe second grade, first grade, wherever you learned to add. Maybe kindergarten anymore. I don't know. But we know what addition is. We know 34 plus 1 equals 35, subtraction. So these are called operators. Okay. The multiplication operator is an asterisk, and the division operator is a slash. So if I say 1.0 divided by 2.0, I get 0.5. 1 divided by 2 is 0.5. Okay. But this one you're probably not familiar with. If you think back to when you first learned division, you didn't do decimals. If you were dividing the number 8 by 3, you would say 2 with a remainder of 2. Okay, 2 times 3 is 6, and there's a remainder of 2 to get to 8. So the percent is actually called the modulus operator, okay, and it gives you the remainder. So if I take 20 divided by 3, it goes in 6 times. 6 times 3 is 18. That means there's 2 left over. So the modulo operator gives me the 2. It tells me how much the remainder is. So that's something that's probably new if you haven't programmed before. Everything else is typical math. Plus, minus, times, division. Now here's something that I alluded to in last week's videos. The last chapter's videos, I should say. And that's integer division. If I'm taking two integers, 5 and 2, and I'm dividing them, you might think the answer is 2.5. But if they're integers, it is not 2.5 because 2.5 is not an integer. So anytime you divide two integers, your result is going to be an integer, and it means it chops off the decimal place. So 5 divided by 2, the answer is 2. Okay. Now, if I say 5.0, now that's not an integer anymore because it's got a decimal place on, so that's a double. And because there's a double involved, it automatically defaults to doing doubles. So 5.0 divided by 2 will give you 2.5. So let's try that. I'm going to bring this over here, system.out.print, and I'm going to say 5 divided by 2. I'm just going to put those right in that print statement. Not going to assign them to a variable or anything. Oops. Didn't want to hit enter. I wanted to hit run. And it prints out 2. But if I say 5.0, which is a double, and divide by 2, I get 2.5. I could also do this. I could say 5 divided by 2.0. And now this is a double. And since there's a double involved, I can get 2.5. So always remember that when you divide two integers, you can only get an integer as a result. And that can create some massive bugs if you don't remember it. You're doing some calculations of some kind and you end up doing two integers and you can't understand why your results are getting rounded or getting the wrong answer. Okay. 5% 2 yields 1, which is the remainder. 2 goes into 5 2 times with a remainder of 1. Let's try that one. 5 modulo, which is the percent sign, 2. I'm going to run it, and I get 1. That's the remainder after you divide 5 by 2. Okay. So remainder, it may sound silly, but it's used a lot in programming. For example, an even number, we can test for even numbers by doing modulo 2. If we do modulo 2, the remainder is going to be, if the remainder comes out 0, we know it's an even number because there's nothing left over. 2 goes in evenly. An odd number modulo 2, the answer is always 1. So we could make it use of that to see if it's an even or odd number. We can use today's Saturday and your friends are going to meet in 10 days. What day is in 10 days? You can find that day is Tuesday using the following expression. We take Saturday the 6th, we add 10 to it, that's the 16th. Take modulo 7, and it comes out to 2. So 6 plus 10 is 16. That's in parentheses, and we follow PEMDAS in programming. So parentheses first, 16 modulo 7 is 2. 2 times 7 is 14, with a remainder of 2. So that tells us this is that second day of the week, and that's Tuesday. Let's look at another one, displaying time. I put this one into NetBeans already, right here. So let's look at what this program is doing. Okay. We set up a scanner, just like we did every other time we've seen a scanner. That's why I said, even if you don't fully understand it, you can repeat it. Okay. You'll eventually get to the point where you do understand it as we talk more and more about object-oriented programming. Okay, so we set up this new scanner, assign it to the variable input so we can talk to it. Okay, we tell the user with the systemout.print, enter an integer for the number of seconds. And we say input, that's the scanner. Say, hey, scanner, get me the next integer. And we assign that to a variable that holds an int. It's called seconds. And then we take seconds, which is an int, divide it by 60, which is an int. So what's the answer going to be? It's going to be an int. It's not going to get a decimal. Okay, so we can find exactly how many minutes are in that number of seconds without having any extra remainder. But then we can also take that same number of seconds and we can do modulo 60, which tells us how many seconds are left over. And we're going to assign that to the remaining seconds. So this finds the whole number of minutes by doing integer division with 60. And this finds the remaining seconds by doing modulo with 60. And we see that a lot where you use integer division along with modulo to get the whole part and the remainder for different things. We've used it for doing animation frames in when we're programming and we have 8 frames of animation. Which frame should be next? We have some kind of counter and we take modulo 8 to see which frame would be next to be displayed. Very useful. And then this is going to print out how many minutes and seconds. Let's run this and test it. Enter an integer for seconds. Let's do 75. 75 seconds is 1 minute because 75 divided by 60 is 1. And 75 modulo 60 has a remainder of 15, and that's how we get the remaining seconds. So integer division and modulus operators. All right, so let's talk about floating point numbers. Calculations involving floating point numbers are approximated because they're not stored with complete accuracy. System.out.println 1.0 minus 0.1 minus 0.1 minus 0.1 minus 0.1 minus 0.1. 1, 2, 3, 4, 5. You would think the answer would be 0.5, and it ends up being 0.500000001, not 0.5. Okay. And if we do systemout.println 1.0 minus 0.9, we get 0.0999998, not 0.1. Integers are always stored precisely. So calculations with integers give you a good result. So know that there can be rounding errors. And so sometimes we have to round to get rid of the rounding errors in programming. All right, exponent operations, math.pow. How do we raise something to an exponent? So let me just come over here and do that. Let's do it this way. Let's go back to our little demo, and we're going to print. Notice there's a capital M on math.pow. Pow is short for power. Okay. And whatever we put in here, it takes 2 arguments. So that pow is a method because it has parentheses. And I'm going to put 2 comma 3, which means take 2 and raise it to the 3rd power. So 2 times 2 times 2. And we get 8. Take 3 and raise it to the 2nd power. So 3 squared. 3 times 3 is 9. What about 3 to the 4th power? It's 81. 3 times 3 times 3 times 3. It's 81. So that's how math.pow works. We use that for exponents. Anytime we need to raise something to a power, we call math. That's a class that's built into Java. It's got a method called .pow, and its only purpose is to take one number and raise it to the power of another number. Okay, and we see examples. 2.5 squared is 6.25. 2.5 to the negative 2nd power is 0.16. Okay, so it'll do a lot of complicated math for us. All right, so let's talk about number literals, because I hinted at it a little bit with integers. So a literal is a constant value that appears directly in the program. For example, 34 or 1 million and 5.0 are literals. When I say 34 and I don't put a decimal after it, the Java compiler automatically wants to treat that as an int. Okay, it looks like it as an int. Okay. If I say 1 million? Looks like 1 million. No commas, makes it hard to read. 1 million, that's an int. And I'm storing it as a long, but remember, long is an integer type. And we know it's an int because it doesn't have a 0.0 after it. But if I put 5.0, now that's a literal, that's a number that is a literal double. The Java compiler automatically looks at that and say, that's a double, because it has a point, it has a decimal point in it. Now we saw back when I was showing you integer division, if I take an integer and add a 0.0 on it, it treats it like a double, because that became a literal double the minute I put the decimal point on it. So anytime you see that word literal, that means we're not talking about the variables. We're talking about a number that appears in our code and what its data type is the way it's written. So an integer literal can be assigned to an integer variable as long as it can fit in the variable. So if my number was too big, it might not fit into a byte, or it might not fit into an int if it was gigantic. Okay, and if it's too large, you get a compilation error. Okay, it doesn't happen very often because ints can hold some pretty big numbers. So if I tried to assign 1,000 to a byte, we'd have a problem because remember, bytes don't go that big. So an integer literal is assumed to be of the int type. So if we see a number without a decimal point, Java automatically assumes it's an int. If we want it to be a long or an L, L is preferred. We use a capital L. You could technically use a lowercase l, but it looks like a 1, so don't do it. So if you see a number in your code with an L after it, that means it's a long literal. Okay, so let me do an example of that real quick. Long my var equals 15. Okay. What if I try 15.7? Doesn't work. What if I put a giant number like that? It works, but that thinks that's an int, and an int doesn't fit. So I put an L after it. I might have went too long. I might have went just a little too far. So if I put an L after it, it says, hey, I don't want you to store this as an int. It's going to be a long. So the L means this is a long literal. Okay. So int literals don't have anything after them. If we put an L, that means it's a long. Okay. Floating point literals are written with a decimal point. By default, a floating point literal, meaning if we see a decimal point, Java says, hey, that's a double. It doesn't say, hey, that's a float. It says, hey, it's a double. Okay. So if we want it to be a float, we have to stick an F, lowercase or uppercase. This in this case, it doesn't really matter if it's lowercase or uppercase because you can't confuse those for a 1 or anything like that. If you want to force something to be a double, you can actually put a D after it. But again, as long as it has a decimal and you don't put anything after it, it gets treated like a double. So 100.2F says, hey, this is a floating point number. 100.2D says this is a decimal. Those are, we designate literal numbers. Variables are designated by the type declaration that we do. All right, double type values are more accurate than floats. So if we do this, system.out.println 1.0 divided by 3.0 is, and then we actually do the math, 1.0 divided by 3, we'll get 0.333, 16 digits. But if we do it with floats, so we got a 1.0 as a float and a 3.0 as a float, when we do the math with it, we only get 7 digits, and so we get a rounding error here. So floats, doubles are more accurate than floats, obviously, because they hold more decimal places if we want them to. And the last thing we're going to talk about in this video is scientific notation. We've covered a lot of different numbers. Floating point literals can also be specified in scientific notation. So if I say 1.23456 and then put the letter E plus 2, that means times 10 to the second power. If you remember you doing scientific notation in any of your science classes, you can also read it, you can just also think of it times 10 to the second power as times 100, or I can move my decimal place over 2 places. So that becomes 123.56. But this is scientific notation. All right, so that's scientific notation. You can use scientific notation anytime you want. The capital E or the lowercase e represents an exponent, which means raise 10 to whatever power we see there.